In this video, I'm going to be going over some of the most common misconceptions about energy in general and how it relates to climate change in particular. In order to do this, we're going to need to start at the beginning. What is energy? Fundamentally, energy is some form of motion, or at the very least, the potential for motion. Kinetic energy is the motion of an entire large object. Thermal energy is the motion of the molecules in something. Electrical energy is the motion of electrons. Light is the maximum speed motion of photons, and so on. Without energy, you literally can't do anything. And the more energy you have, the more stuff you can do. This is true in theoretical physics, and it remains just as true when we talk about the role of energy in society. This means energy is also the base unit of the economy, because some energy must be expended in order for any economic activity to occur. Food is energy, cleaning water takes energy, shipping things around takes energy, building anything takes energy, mining and working the materials needed to build anything takes energy, heating a room takes energy, driving a car takes energy, computers take energy, doing literally anything takes energy. In basically every attempted measurement of human prosperity, you will find an almost one-to-one correlation between prosperity and energy consumption. For example, poverty rates decrease as energy consumption increases. Even more abstract criteria, like the Human Development Index, which looks at things like average life expectancy and number of years spent in school, show an extremely tight correlation with energy consumption. Now, as a counter argument to that, you will hear some people say that's only true up to a certain point, and then that correlation begins to fall off. The correlation on some of these metrics will sometimes fall off at the very upper end because the metric basically defines what enough is to be whatever is plausible for most people to do with X amount of energy consumption. So of course, being able to do more than that isn't going to show up on your metric. But what we consider necessities also progresses with energy consumption. This just tends to happen on a longer time frame with generational order of magnitude jumps in energy availability. Today in a developed country, you'd likely consider things like rapid transportation, a computer, climate-controlled shelter, internet access, advanced medical tests and treatment, and many more things to be necessities. But the only reason it's possible for these things to be considered necessities is because of massive increases in energy consumption. So basically, the metrics can't account for any new technology, any new stuff we might want to do that would require an increased energy consumption. And then they'll use those metrics that they made to make the argument that, well, things couldn't possibly be any better than looking at how they are in countries that are around this level of energy consumption. So therefore, there's no point in ever consuming more energy. When in fact, I think most people understand that we have not invented everything that will ever be invented, and this trend of increased energy consumption correlating with increased prosperity, among other things, will continue well into the future. So hopefully that got across why it's such a big deal to suggest reducing energy consumption. Even small acts of energy conservation cause huge reductions in prosperity, and any significant amount of energy conservation causes widespread death. So I'm trying to contextualize this before getting to the elephant in the room here, which is obviously global warming, because that's where most of the time today you're seeing energy conservation attempt to be justified in order to prevent global warming. Now, the underlying physics behind climate change is actually very simple, but I think it's pretty clear that the vast majority of climate activists or the politicians or bureaucrats who are pushing some kind of climate agenda don't have any understanding of it whatsoever. So in order to continue with this explanation, I'm going to quickly go over the thermodynamics behind global warming. All bodies in a vacuum have a thermal equilibrium, which is purely a function of radiation, the radiation hitting them and the radiation they emit. By radiation, I mean light, including visible light. The Earth is a body in a vacuum, so this applies to the Earth. All matter both absorbs and emits light. When it absorbs light, the light is converted to heat in the object that absorbed the light. When it emits light, the heat in that object is converted to light. The simplest form of this thermal equilibrium would be if all bodies were pure black bodies. This means they perfectly absorb all light, and they emit light as described by Planck's law. The distribution of wavelengths or color of light emitted by an object is determined by the object's temperature. When you see 2700K or 5000K on a light bulb, it is saying the light bulb produces a color similar to the color that would be produced by a black body at the temperature shown in Kelvin. If there were only black bodies, or if the Earth were a black body, there would be no way to change the thermal equilibrium of the Earth. There would be no potential for global warming. But in the real world, many things are not black bodies, including the Earth. Many surfaces absorb or emit light very well at certain wavelengths and very poorly at others, or are transparent to light at certain wavelengths and reflective or absorbent at others. When a gas is transparent to visible light, or the light predominantly emitted by the sun, but absorbs thermal infrared, or the light predominantly emitted by things that are vaguely near room temperature, like the Earth, it's called a greenhouse gas. This is because it allows light from the sun to pass through and get absorbed by the Earth, but then stops it from getting emitted back into space, thus raising the thermal equilibrium temperature of the Earth. By far the most common greenhouse gas is water, but then carbon dioxide. So I haven't extensively studied Earth's climate, but based on that very basic thermodynamic analysis, there's no reason to doubt that putting more carbon dioxide into the atmosphere would increase the thermal equilibrium of the Earth. But regardless of how much damage you think global warming is going to do to the world, none of this means that the bundle of policies being packaged as a climate agenda, which generally includes a lot of degrowth or static growth or energy conservation schemes, makes any sense at all. And there are three main reasons for that. Reason number one, the damage done to the world by any remotely substantial amount of energy conservation would be far greater than the damage done by global warming, even according to the worst projections. Reason number two, energy conservation schemes will never be enough to have a meaningful impact on the rate of global warming. In order to have a meaningful impact, you'd have to do something like cut energy use by 50, 60, 70%, which would, it would destroy human society if you actually tried to do what you would need to do in order to stop global warming. It would destroy human society. Reason number three, it would be easy to change the thermal equilibrium and therefore the average temperature of the Earth if there were massive increases in the amount of energy available to humans. This would likely just mean removing CO2 from the atmosphere, which is not technically challenging, it just takes a significant amount of energy. The best way to stop us from developing the technology needed to make this energy available is to force all these energy conservation schemes on people. All they'll do is destroy economies and cripple development of everything, including actual methods of changing the Earth's climate. So the only way I can see to justify the disastrous consequences of energy conservation schemes is if you believe that we're approaching some fundamental bottleneck in energy availability that can't be overcome through technological progress. And this is the fundamental false premise at the root of the climate agenda. I said it's a false premise that we're approaching a potential bottleneck in energy availability. So now let me show you why that is. Most of the numbers I'm going to show, in order to keep it even across everything and reduce that complexity here, are going to be if all of these resources were harvested with perfect efficiency. Again, this is obviously not going to be the case, but it also doesn't matter because if your efficiency is 10 or 20%, it still doesn't really affect the overall point, which is the huge order of magnitude type increases that I'm talking about here. We currently consume 177,000 terawatt hours of energy on Earth every year. Geothermal and hydro can't really make a dent in that. In fact, we're actually pretty close to the practical limits of how much hydropower we can extract already. All the wind in the world is similar to the current consumption rate, but of course to extract that we would need to stop all wind on the planet, including over the ocean. So I would say that for the most part, all these resources are pretty useless. If they happen to be conveniently available and concentrated, there's not much reason not to harvest them, but they shouldn't be any kind of large-scale long-term fixation. Now let's compare that to energy from the sun. As you can see, energy available directly as light from the sun dwarfs all of these. Except this is actually just the solar energy that hits New Mexico every year. For those of you who don't know, that's a relatively small US state. The fissionable isotope of uranium is uranium-235, but most uranium on Earth is uranium-238. However, U-238 can be transmuted into plutonium in a U-235 nuclear fission reactor. This plutonium can then also be used as fuel for a fission reactor, so it can increase the amount of potential fuel for fission reactors since there is a lot more U-238 on Earth than U-235. I'm not sure what the theoretical limit on this U-238 transmutation is, so I picked a number that is significantly higher than anything anyone has ever achieved to try to make it in line with my theoretical limit numbers for the other sources. The number shown here is if you were to fission all U-235 available on land in a 3.5x breeder reactor. The current state-of-the-art fusion reactor, the one with all that news hype from earlier this year, is a tritium-deuterium reactor. Tritium and deuterium are isotopes of hydrogen, and it's the easiest fusion reaction to sustain, mostly because it can be done at relatively low temperatures compared to most fusion. The problem is tritium is pretty unstable, meaning it decays over a fairly short period of time and turns into helium. So there's not really any tritium just laying around. The stuff they're using in these fusion reactor experiments is tritium made in uranium fission reactors. The theoretical solution to this is to use tritium-deuterium fusion reaction to transmute lithium into tritium. I don't know what efficiency changes there would be in doing this, but for the sake of these numbers, we're going to assume the same output as if all that lithium were just tritium. That shouldn't be too far off in theory. This can only be done with the lithium-6 isotope, which is about 5% of the lithium on Earth, so we'll only be looking at that. Natural hydrocarbon fuels are naturally occurring fuels that are harnessed by oxidizing the hydrogen and/or carbon in them, so coal, oil, and natural gas, which is mostly methane. Uranium, lithium, and hydrocarbons are shown in total available on Earth, whereas the sun in New Mexico is shown as the yearly total. So in other words, the hydrocarbon and nuclear fuels on this chart combined are equivalent to about 30 years of sun in New Mexico. What if we look at just the sun that hits buildings that already exist? That's actually about 3% of land on Earth. That's pretty similar to the total amount of hydrocarbons remaining on Earth. This is a very realistic energy availability from the sun on Earth without doing anything extravagant like offshore solar farms or anything like that. This is covering current buildings and some smallish percentage of the world's deserts. The number isn't exact because it depends on the desert. Or alternatively, some desert and a little more of some less optimal terrain like tundra or some other combination. That is 200x current yearly consumption, 2 orders of magnitude. The right technology to do this is not publicly available at this time, but let's just be very conservative here and say that we can only utilize this at 20% efficiency. It's still a 40x increase over current consumption. Now, to get the sun more in line with the other theoretical numbers, this is the light that hits all land on Earth. You can see current consumption is now almost invisible. Now all sun on Earth, including the oceans, compared to all uranium on Earth. Obviously, it would not be practical to extract all uranium out of the ocean, just as it would not be practical to cover the entire Earth in solar panels, although both are theoretically possible. Once again, this is comparing yearly sun to all uranium there will ever be, so even seawater uranium is probably not super interesting when compared to solar energy on Earth. It may have some uses for space travel, depending on what the requirements for lithium fusion end up being. What is interesting is transmuted lithium fusion, as I discussed earlier, using lithium from the sea. Almost all lithium on Earth is also in the ocean. You could extract the same amount of energy from it as about 10 years of sun, or 10 times what is available in seawater uranium. Of course, in addition to not being able to extract it all, there are many other demands for lithium, but the general point of energy availability remains the same. With seawater lithium fusion, we could increase our energy consumption by another 50 times or so, in addition to the 100 to 200 times we can ultimately get from the sun, while still leaving plenty of time to move towards the generational leap after this one. So I think a total of 150 to 250x increase in energy consumption over the next 100 years is very realistic. Although I do think that pretty much all lithium fusion energy should be used for space travel. So what's the next 100 to 1000x increase after that? This is the energy from fusing all deuterium on Earth, compared to harvesting 1% of the sun's energy for 10 years. Not 1% of the sun's energy that hits Earth, 1% of the sun's total energy output. I picked 1% because it seems it may actually be possible given the amount of usable mass in the solar system, and I picked 10 years to show the rough equivalence to deuterium fusion. Obviously, being at the end of the chain here, these are the ideas that are the least explored and furthest from being practical. But I just wanted to throw it in to make it clear that we're still not going to run into fundamental energy bottleneck after the next generational development. This would bring us to be able to sustain about 1 billion times current consumption, 9 orders of magnitude increase. And just for fun, here's all the sun's energy. Of note is that deuterium fusion is still visible on this chart, which is pretty cool. All of the resources I just showed are things that we have solid physical models of. We don't have the technology to cost effectively harvest them yet, but we have the theoretical understanding of the resources. And even just looking at those resources, you can see a clear path where our current level of energy consumption becomes virtually indistinguishable from zero. So how do we start heading down this path and getting these generational leaps in energy consumption? Well, we do need to get rid of the roadblocks and allow actual open competition. And then we need competent engineering. There is no other option. We need solid first principles R&D to develop the technologies capable of harnessing these resources cost effectively. And there is no other solution. And the point of doing this is not to solve global warming. The point of doing this is the increase in the energy availability itself and all of the things that that's going to unlock and the massive increase in prosperity that that's going to bring. And solving global warming will just be an inherent byproduct of doing what we should be doing anyway.